Welcome to this module on three-phase induction motor. Sound control. You can use this to adjust the volume. Pre-assessment. By the end of this module, you will be able to explain principle and working of three-phase induction motor, give details of construction of three-phase induction motor, list types of three-phase induction motor rotors along with the construction, and explain characteristics of three-phase induction motor. Click Next to continue. With this, we are done with the single-phase induction motor. Now comes the three-phase induction motor. Click Next to continue. Here are 4 questions related to three-phase induction motor. First, what is rotating magnetic field? Second, why is three-phase induction motor self-starting? Third, what is the working principle of three-phase induction motor? And fourth, why are they so common in industry? Click each to know the answer. Balanced three-phase winding that is mechanically displaced by 120 degrees from each other, fed by balanced three-phase source, a rotating magnetic field with constant magnitude is produced, rotating with a constant speed called synchronous speed, which is given by the following formula: Ns equals 120 Fe upon P rpm, where Ns is synchronous speed, Fe is supply frequency, P is the number of poles, and rpm, that is revolutions per minute, is unit of speed. The waveforms showing the balanced AC supply and black arrow is showing the corresponding rotation of magnetic field. Click Next to continue. We know that the AC supply is a sinusoidal wave and it produces pulsating magnetic field in uniformly distributed stator winding. Since pulsating magnetic field can be assumed as two oppositely rotating magnetic fields, there will be no resultant torque produced at the starting, and due to this, the motor does not run. After giving the supply, if the rotor is made to rotate in either direction by external force, then the motor will start to run. This problem has been solved by making the stator winding into two windings. One is main winding and other is auxiliary winding, and a capacitor is fixed with the auxiliary winding in series. This will make a phase difference when current will flow through the both coils. When there will be phase difference, the rotor will generate a starting torque and it will start to rotate. Practically, we can see that the fan does not rotate when the capacitor is disconnected from the motor. But if we rotate it with hand, it will start to rotate. So, this is the reason of using capacitor in the single-phase induction motor. In three-phase system, there are three single-phase lines with 120-degree phase difference. So, the rotating magnetic field is having the same phase difference, which will make the rotor to move. If we consider three phases, A, B and C, when phase A is magnetized, the rotor will move towards the phase A winding. In the next moment, phase B will get magnetized and it will attract the rotor, and so the phase C. Hence, the rotor will continue to rotate. The direction of rotation of induction motor can easily be changed by changing the sequence of three-phase supply. That is, if RYB is in forward direction, the RBY will make the motor to rotate in reverse direction. Click Next to continue. Practically, we can see that the fan does not rotate when the capacitor is disconnected from the motor. But if we rotate it with hand, it will start to rotate. So, this is the reason of using capacitor in the single-phase induction motor. In three-phase system, there are three single-phase lines with 120-degree phase difference. So, the rotating magnetic field is having the same phase difference, which will make the rotor to move. If we consider three phases, A, B and C, when phase A is magnetized, the rotor will move towards the phase A winding. In the next moment, phase B will get magnetized and it will attract the rotor, and so the phase C. Hence, the rotor will continue to rotate. The direction of rotation of induction motor can easily be changed by changing the sequence of three-phase supply. That is, if RYB is in forward direction, the RBY will make the motor to rotate in reverse direction. Click Next to continue. The stator of the motor consists of overlapping winding offset by an electrical angle of 120 degrees. When the primary winding or the stator is connected to a three-phase AC source, it establishes a rotating magnetic field which rotates at the synchronous speed. From the working principle of three-phase induction motor, it may be observed that the rotor speed should not reach the synchronous speed produced by the stator. If the speed equals, there would be no relative speed, so no EMF would be induced in the rotor and no current would be flowing, and therefore no torque would be generated. Consequently, the rotor will not be able to reach the synchronous speed. The difference between the stator or synchronous speed and rotor speeds is called the slip. Click Next to continue. Three-phase induction motor are very common because of the following points. Simple in construction, it has only one moving part. It doesn't have brush gear and commutator. Now comes with VSD technology, that is, variable speed drive. Click Next to continue. Click Next to continue. Three-phase induction motor has two main parts, stator and rotor. Click each to get an overview. As its name indicates, stator is a stationary part of induction motor. A stator winding is placed in the stator of induction motor and the three-phase supply is given to it. The rotor is a rotating part of induction motor. The rotor is connected to the mechanical load through the shaft. The rotor of the three-phase induction motor is further classified as squirrel cage rotor, slip ring rotor or wound rotor or phase wound rotor. Depending upon the type of rotor construction used, the three-phase induction motor is classified as squirrel cage induction motor and slip ring induction motor or wound induction motor or phase wound induction motor. Click Next to continue. As the starter part of both type of three-phase induction motor is same, let us understand its construction. The stationary electrical part of the motor. The starter core of a National Electrical Manufacturers Association, that is, NEMA motor is made up of several hundred thin laminations. Starter laminations are stacked together, forming a hollow cylinder. Coils of insulated wire are inserted into slots of the starter core. Electromagnetism is the principle behind motor operation. Each grouping of coils, together with the steel core it surrounds, form an electromagnet. The starter windings are connected directly to the power source. Click Next to continue. The starter has three following parts: starter frame, starter core, and starter winding. Click each circle to know more. The main function of the starter core is to carry alternating flux. In order to reduce the eddy current losses, the starter core is laminated. This laminated type of structure is made up of stamping, which is about 0.4 to 0.5 millimeter thick. All the stamping is stamped together to form starter core, which is then housed in starter frame. The stamping is generally made up of silicon steel, which reduces the hysteresis loss. The slots on the periphery of starter core of the three-phase induction motor carries three-phase windings. This three-phase winding is supplied by three-phase AC supply. The three phases of the winding are connected either in star or delta depending upon which type of starting method is used. The squirrel cage motor is mostly started by star-delta starter, and hence the starter of squirrel cage motor is delta connected. The slip ring three-phase induction motor are started by inserting resistances, so the starter winding can be connected either in star or delta. The winding wound on the starter of three-phase induction motor is also called field winding, and when this winding is excited by three-phase AC supply, it produces rotating magnetic field. Starter frame is the outermost part of the three-phase induction motor. Its main function is to support the starter core and the field winding. It acts as a covering and provides protection and mechanical strength to all the inner parts of the machine. The frame is either made up of die-cast or fabricated steel. The frame of three-phase induction motor should be very strong and rigid, as their air gap length of three-phase induction motor is very small. Otherwise, rotor will not remain concentric with stator, which will give rise to unbalanced magnetic pull. Click Next to continue. Now, as we know that based on the type of rotors, there are two types of three-phase induction motors: squirrel cage induction motor and slip ring induction motor. Click each circle to know more. The rotor of the squirrel cage 3-phase induction motor is cylindrical in shape and have slots on the periphery. The slots are parallel to each other and are a bit skewed to prevent magnetic locking of the stator and rotor teeth and makes the working of motor more smooth and quiet. The squirrel cage rotor consists of aluminium, brass or copper bars that are placed in the slots on the periphery of the rotor. The rotor conductors are permanently shorted by the copper or aluminium rings called the end rings, forming a complete closed circuit resembling like a squirrel cage, hence the name squirrel cage induction motor. The absence of slip ring and brushes make the construction of squirrel cage 3-phase induction motor very simple and robust and hence widely used as 3-phase induction motor. These motors have the advantage of adapting any number of pole pairs. The squirrel cage rotor winding is made symmetrical. As the bars are permanently shorted by end rings, the rotor resistance is very small and it is not possible to add external resistance as the bars are permanently shorted. Click Next to continue. Apart from the body, stator, core, winding, insulation and rotor, the following are the main components of squirrel cage induction motor: terminal box, connecting terminal plate, ball bearing, drive end, fitted key or keyway, shaft, end shield, drive end, housing, foot block, fan shroud, fan. Click Next to continue. Aren't you curious to know about squirrel cage rotor? Click the thumbs up to know more. This is the squirrel cage rotor. Click the image to go inside the rotor. The rotor conductors of a squirrel cage induction machine are aluminium bars connected to rings that short the ends together. These conductors are formed by casting molten aluminium into slots in the laminated iron rotor. And these are the parts of squirrel cage rotor. Click Next to continue. NEMA, the National Electrical Manufacturers Association in United States and IEC in Europe, has classified the design of the squirrel cage induction motors based on their speed torque characteristics into some classes. These classes are Class A, Class B, Class C, Class D, Class E and Class F. This class is for high starting torque, low starting currents and low slip at the full load, that is less than 5%. Up to 250% of the full load torque, the starting torque is in this class of design. The pull-out torque is lower than that for Class A induction motors in this design. The motors are built from double cage rotors. They are more expensive than motors of Class A and B classes. Class C designs are used for high starting torque loads like loaded pumps, compressors, and conveyors. This class is for very low starting torque, normal starting current, and low slip. Compensator or resistance starter are used to control starting current. This class is for low starting torque, 1.25 times of full load torque when full voltage is applied, low starting current, and normal slip. Click Next to continue. This class is for low starting torque, 1.25 times of full load torque when full voltage is applied, low starting current, and normal slip. In this class, motors have very high starting torque of around 275% or more of the rated torque. The motors of this class have low starting current and high slip at full load. Also, in this class of design, the high rotor resistance shifts the peak torque to a very low speed. It is even possible at 0 speed or 100% slip for the highest torque to occur in this class of design. Full load slip, which is typically 7 to 11%, but may go as high as 17% or more, is quite high in this class because of the high rotor resistance. This class is for high starting torque, low starting currents, and low slip at the full load, that is less than 5%. Up to 250% of the full load torque, the starting torque is in this class of design. The pull-out torque is lower than that for Class A induction motors. In this design, the motors are built from double gauge rotors. They are more expensive than motors of Class A and B classes. Class C designs are used for high starting torque loads like loaded pumps, compressors, and conveyors. This class is for normal starting torque, normal starting current, and low slip. In this class, pull-out torque is always of 200 to 300% of the full load torque, and it occurs at a low slip, that is less than 20%. For this class, the starting torque is equal to rated torque for large motors and is about 200% or more of the rated torque for the smaller motors. This class is for normal starting torque, lower starting current, and low slip. Motor of this class produces about the same starting torque as the Class A induction motor. Pull-out torque is always greater than or equal to 200% of the rated load torque. But it is less than that of the Class A design because it has increased rotor reactance. Again, rotor slip is still relatively low, that is less than 5% at full load. Applications of Class B design are similar to those for Design A, but Design B is preferred more because of its lower starting current requirements. In this class, motors have very high starting torque of around 275% or more of the rated torque. The motors of this class have low starting current and high slip at full load. Also, in this class of design, the high rotor resistance shifts the peak torque to a very low speed. It is even possible at 0 speed or 100% slip for the highest torque to occur in this class of design. Full load slip, which is typically 7 to 11%, but may go as high as 17% or more, is quite high in this class because of the high rotor resistance. This class is for very low starting torque, normal starting current, and low slip. Compensator or resistance starter are used to control starting current. This class is for low starting torque, 1.25 times of full load torque when full voltage is applied, low starting current, and normal slip. Click Next to continue. Here are characteristics of NEMA B sequence cage induction motor. Locked rotor amperes can be 4 to 8 times of full load amperes. Starting torque can be from 80 to 275% of full load torque. Breakdown torque can be from 175 to 300% of full load torque. Click Next to continue. In this type of three-phase induction motor, the rotor is wound for the same number of poles as that of stator, but it has less number of slots and has less turns per phase of a heavier conductor. The rotor consists of numbers of slots and rotor windings are placed inside these slots. The three end terminals are connected to form star connection. At starting, the resistances are connected in rotor circuit and is gradually cut out as the rotor pick up its speed. When the motor is running, the slip rings are shorted by connecting a metal collar which connect all slip rings together, and the brushes are also removed. This reduces wear and tear of the brushes. Due to presence of slip rings and brushes, the rotor construction becomes somewhat complicated. Therefore, it is less used as compared to squirrel cage induction motor. As its name indicates, it consists of slip rings connected on same shaft as that of rotor. The three ends of three-phase windings are permanently connected to these slip rings. The slip rings are insulated from each other and the rotor shaft. The brushes are used to carry current to and from the rotor winding. These brushes are further connected to three-phase star-connected resistances. The external resistance can be easily connected through the brushes and slip rings and hence can be used for speed control and improvement of the starting torque of the motor. Click Next to continue. Click Next to continue. To refresh our knowledge of both squirrel cage induction motor and slip ring induction motor, let us quickly go through the difference between them. 1. Construction of slip ring induction motor is complicated due to presence of slip ring and brushes, whereas the construction of squirrel cage induction motor is very simple. Second, here the rotor winding is similar to the stator winding, but in squirrel cage induction motor, the rotor consists of rotor bars, which are permanently shorted with the help of end rings. 3. In slip ring induction motor, we can easily add rotor resistance by using slip ring and brushes. But in squirrel cage, since the rotor bars are permanently shorted, it is not possible to add external resistance. 4. In slip ring induction motor, due to presence of external resistance, high starting torque can be obtained. But here, the starting torque is low and cannot be improved. 5. Here, the slip ring and brushes are present, which is not the case with squirrel induction motor. 6. Frequent maintenance is required due to presence of brushes in slip ring induction motor, whereas squirrel cage induction motor requires less maintenance. Click Next to continue. 7. As the construction is complicated, cost is also higher than the squirrel cage induction motor. 8. The slip ring induction motor is rarely used. Only 10% industry uses slip ring induction motor, whereas the squirrel cage induction motor is widely used. 9. Due to high rotor copper losses, efficiency of slip ring induction motor is lower in comparison to its counterpart. 10. Speed control by rotor resistance method is possible in slip ring induction motor, but not in squirrel cage induction motor. 11. Slip ring induction motor is used where high starting torque is required, like in hoists, cranes, elevator, etc. Whereas squirrel cage induction motor is used in lathes, drilling machine, fan, blower printing machines, etc. Click Next to continue. In the next segment of this module, let us understand the following concepts: slip, rotor speed and torque. Click each to know more. As we already know that the induction motor will always run at a speed lower than the synchronous speed, the difference between the motor speed and the synchronous speed is called the slip speed, where n slip equals slip speed, n sync equals speed of the magnetic field, and nm equals mechanical shaft speed of the motor. Also, the percent difference of the motor speed and the synchronous speed is called slip, where ns is synchronous speed in rpm, nr is mechanical speed of rotor in rpm. Under normal operating conditions, the value of s is around 0.01 to 0.05, which is very small, and the actual speed is very close to synchronous speed, but s is not negligible. If the rotor runs at synchronous speed, then s equals to 0, and if the rotor is stationary, then s equals to 1. The slip is a ratio and hence doesn't have units. Click Next to continue. Let us check your understanding. Click Next to continue. When the rotor moves at rotor speed nr/rps, the stator flux will circulate the rotor conductor at a speed of ns minus nr per second. Hence, the frequency of the rotor is written as following. When the rotor is blocked, that is S equals to 1, the frequency of the induced voltage is equal to the supply frequency. On the other hand, if the rotor runs at synchronous speed, that is S equals to 0, the frequency will be 0. The frequency of the voltage induced in the rotor is given by the following equation, where Fr is the rotor frequency in Hertz, P is number of stator poles, and N is slip speed in RPM. Click Next to continue. While the input to the induction motor is electrical power, its output is mechanical power, and for that we should know some terms and quantities related to mechanical power. Any mechanical load applied to the motor shaft will introduce a torque on the motor shaft. This torque is related to the motor output power and the rotor speed as shown in the following equations. Click Next to continue. Another unit used to measure mechanical power is the horsepower. It is used to refer to the mechanical output power of the motor. Since we, as electrical engineers, deal with watts as a unit to measure electrical power, there is a relation between horsepower and watts. 1 horsepower is equal to 746 watts. Click Next to continue. Following is the standard equation for torque. Starting torque is the torque produced by induction motor when it is started. We know that at start the rotor speed n is 0 and the slip becomes 1. So The torque equation becomes as mentioned. Click Next to continue. The starting torque is also known as standstill torque. Now differentiate the above equation by using division rule of differentiation. On differentiating and after putting the terms equal to 0, we get. Click Next to continue. Note, at starting, S equals to 1, so the maximum starting torque occur when rotor resistance is equal to rotor reactance. Click Next to continue. Click Next to continue. Let us check your understanding. Question. A 208 volts, 10 horsepower, 4-pole, 60 Hz star connected induction motor has a full load slip of 5%. Write the answers of the following questions in the respective blank boxes. What is the synchronous speed of this motor? What is the rotor speed of this motor at rated load? What is the rotor frequency of this motor at rated load? What is the shaft torque of this motor at rated load? Click Next to continue. Now, since we know the relation between torque and speed, let us understand the torque-speed characteristics. This is the torque-speed graph. Let us understand it with the following points. 1. The induced torque is 0 at synchronous speed. 2. The curve is nearly linear between no load and full load. In this range, the rotor resistance is much greater than the reactance. So the rotor current torque increases linearly with the slip. The maximum possible torque that can't be exceeded is called pull-out torque and is 2 to 3 times the rated full load torque. 4. The starting torque of the motor is slightly higher than its full load torque. So the motor will start carrying any load it can supply at full load. 5. The torque of the motor for a given slip varies as the square of the applied voltage. 6. If the rotor is driven faster than synchronous speed, it will run as a generator, converting mechanical power to electrical power. Click Next to continue. As we already know the torque equation, let us see how the shape of curve varies with the rotor frequency. During starting, R2 is much less than X2 because rotor frequency is equal to supply frequency. Hence, curve is parabolic during beginning. During running, torque is inversely proportional to the slip. R2 is much greater X2 as rotor frequency is much lesser. Torque becomes directly proportional to speed and hence the curve also becomes a straight line. Click Next to continue. Do you know that a three-phase induction motor can also work as a generator? I know it is interesting. To understand it, let us first learn about the torque-slip characteristics of three-phase induction motor. The torque-slip curve for an induction motor gives us the information about the variation of torque with the slip. The slip is defined as the ratio of difference of synchronous speed and actual rotor speed to the synchronous speed of the machine. The variation of slip can be obtained with the variation of speed, that is, when speed varies, the slip will also vary and the torque corresponding to that speed will also vary. The torque-slip characteristic curve, as shown, can be divided roughly into three regions: braking region, motoring region, generating region. Click Next to continue. With torque-slip characteristics, we got to know that there are three following modes of a three-phase induction motor: motoring mode, generating mode, and braking mode. Click each to learn more. In this mode of operation, supply is given to the stator sides and the motor always rotates below the synchronous speed. The slip varies from 0 to 1. It is 0 at no load and 1 at standstill. From the curve, it is seen that the torque is directly proportional to the slip. That is, more is the slip, more will be the torque near synchronous speed. In this mode of operation, induction motor runs above the synchronous speed and it should be driven by a prime mover. The stator winding is connected to a three-phase supply in which it supplies electrical energy. In this case, the torque and slip both are negative, so the motor receives mechanical energy and delivers electrical energy. Induction motor is not much used as generator because it requires reactive power for its operation. In the braking mode, the two leads or the polarity of the supply voltage is changed so that the motor starts to rotate in the reverse direction and as a result the motor stops. This method of braking is known as plugging. This method is used when it is required to stop the motor within a very short period of time. The kinetic energy stored in the revolving load is dissipated as heat. Also, motor is still receiving power from the stator, which is also dissipated as heat. As a result, motor develops enormous heat energy. For this, stator is disconnected from the supply before motor enters the braking mode. If load which the motor drives accelerates the motor in the same direction as the motor is rotating, the speed of the motor may increase more than synchronous speed. In this case, it acts as an induction generator which supplies electrical energy to the mains, which tends to slow down the motor to its synchronous speed. In this case, the motor stops. This type of braking principle is called dynamic or regenerative braking. Click Next to continue. Post-assessment.
you